Today we're tackling a design problem, building an ordered stream. The challenge is to reconstruct a sequence from fragmented, out-of-order data. How do you ensure you only release continuous chunks, even when pieces arrive late? We need to implement a class that receives pairs of an ID and a value. IDs are unique and range from 1 to n. The goal is to return a list of values whenever we can form a contiguous block, starting from the current expected ID. If an insert doesn't complete a contiguous block, we return an empty list. A straightforward approach uses a dictionary to store the incoming ID value pairs. Each time we insert, we add it to the dictionary. Then, we check if the current pointer's ID exists. If it does, we add its value to our result and increment the pointer, repeating this until we hit a missing ID or the end of the stream. While this works, repeatedly checking contains key in a dictionary can be slightly less efficient than direct access. This gives us big O of n total time for n inserts, big O of 1, constant time amortized per insert, and big O of n space. The key insight for optimization is realizing that our IDs are sequential integers from 1 to n. This means we don't need a full-fledged dictionary. An array can perfectly map IDs to their values. We'll declare a string array of size n plus 1, using index 0 as a dummy. We also maintain a pointer, initialized to 1, representing the next expected ID. When an insert call comes in, we simply place the value directly into our array at the given ID index. After placing the value, we enter a loop. As long as our pointer is within array bounds and the element at the pointer's index is not null, we add that element to our result list and increment the pointer. This direct array access is faster than dictionary lookups. Let's trace with n equals 5. Initially, our array is empty and the pointer is 1. If we insert ID 3 with value CCCCC, we place CCCCC at index 3. The pointer is still 1, so no contiguous block forms, and we return an empty list. Next, inserting ID 1 with AHA puts it at index 1. Now the pointer is 1 and stream 1 is AHA. We add AHA to our result and increment the pointer to 2. Stream 2 is still null. Inserting ID 2 with BBBBB fills index 2. Now stream 2 is BBBBB, so we add it and increment the pointer to 3. Stream 3 is CCCCC, so we add it and increment the pointer to 4. Stream 4 is null, so the loop stops. We return BBBBB, CCCCC. Eventually, after all inserts, the array will be fully populated. The final output is correct because the pointer ensures we only emit values when they form an unbroken sequence from the current expected ID. You'll spot this pattern when you have sequential integer IDs, especially starting from 1, and need fast direct access. It's also useful when you're looking to process data in order, even if it arrives out of sequence, and want to avoid the overhead of a HashMap when indices are dense. Time complexity is big O of n total for n inserts, amortized big O of 1, constant time per insert. Space complexity is big O of n for storing the stream. This array as a HashMap pattern is a simple yet powerful optimization. Try the next problem, same pattern. Don't forget to like and subscribe for more DSA insights.